Morning students, in the previous video session you have gone through angle of repose and its examples. Also you have learned the ways to reduce the friction in machines and all. And today we can see a new topic about the dynamics of circular motion. So dynamics of circular motion, that is our topic. So this is a topic which is different from the previous lessons and all. And in the previous lessons and all, we have learned about how to apply the Newton's laws in the linear motions. And we applied the Newton's law in linear motion, and we have found some equation, and we have derived some derivation and all. But this circular motion, it is something different. We can tell that we know that it is an important motion. It is very useful in our daily life also. In our daily life, we came across many of these type of circular motions and all. And when we studied about the linear motion, we know that a particle can be moved with the force or without the force. That also we have gone through some of the experiment which is given by the scientist in the second unit starting and all. We have came across that experiment, and here that Galileo's experiment we have seen how an object can be moved without a force, and linear motion is occurring without a force. That is what we have seen through that experiment, and here we are studying about the circular motion, and we are applying this Newton's law during this motion. Actually, there is no Newton's first law for circular motion, but we can apply the Newton's second law, F is equal to ma in circular motion as well. And we know that circular motion which is occurring due to the force, and because of this force, it can change the velocity of the particle in different ways. We know that a force, suppose a force is acting on a moving object, that force can able to change that velocity of that object in three different ways, or during this time the motion will be different. You can see that three ways. The first way is we can change the magnitude of the velocity without changing the direction of the velocity. Assume that one ball we are throwing, football case not one ball we are throwing. Assume that you are throwing a ball, and you have thrown one ball with a different magnitude or different speed or different power, you can tell, and your friend is throwing the same ball but with the different size, or you can tell the magnitude of the velocity he is changing, but in the same direction he is throwing that ball. So without changing the direction of that velocity, in the same direction we are throwing something. So what we can see means we can see that particle which is moving in a straight direction or same direction, but with the acceleration we can see. For example, you can tell that you are kicking a ball, a football you are kicking in the same direction, your friend is kicking with a different magnitude. So if they are not changing the direction, we can see that the ball will move in the straight line, or in the same direction only ball will move. This is the first way. So what happened means the velocity of the object, the magnitude of the velocity of the object is changing, but not changing the direction of this velocity. So there is one way, and you can tell that some other example also. Assume that one particle which is moving vertically downward direction, so that you can see that in the same direction only it will move. It will not change the direction, but the magnitude. One particle moving downward direction, you can see that when it is coming downward direction, its speed will increase. So the magnitude of velocity is increasing. The magnitude of velocity is changing, but it is not changing the direction. The same direction only it is moving. Also, you can see that a bike. You know that a bike moving in a straight road with acceleration. You can see that suppose when we are traveling through the bypass road and all, what in a straight road we will travel with some acceleration, but we are not changing the direction. We move in the straight line in the same direction, but every time the velocity is changing. Maybe the speed will increase, maybe the speed will decrease. This is a thing which is and all happening during this motion. So the first thing is the magnitude of the velocity can be changed without changing the direction. And the second thing is the direction of motion alone be changed. Only we are changing the direction of motion, but without changing the magnitude. So you know that while playing football and all, not the football, assume that one object which is or not football, what you can tell means some object which is moving in a circular motion. So every time what is happening means its direction is changing. That's what it is showing, circular motion, but it is not changing the velocity. For example, sometimes we know that the bike driveways are there. So sometimes we know that some people, they will try to skid their bike in a circular motion. So while they are doing this thing, we know that the bike moves in circular motion. So always the direction of the motion is changing, but maybe the velocity they are applying is same. That is a thing. Or you can see in some of the exhibition center and all, you can see this Marana Kenar. In that you can see that many bikes will be there, cars will be there. So all which is moving in the same velocity, but every time you see that it is changing the direction of that motion. So changing the direction of motion alone, but magnitude of the velocity is not changing. You can see that it will move in a uniform circular motion. It is one of the best example you can illustrate, you can tell for this second point. So the direction of motion alone be changed without changing the magnitude. So we will get a uniform circular motion. And the third thing is both the direction and the magnitude of the velocity can be changed, so that we will get a non-uniform circular motion. Actually, for example, if we are saying that we can tell that oscillation of a swing or simple pendulum, we know that grandfather's clock and all on simple pendulum will be there. That simple pendulum, we know that it will go one side, then it will come back. So this is a motion of that simple pendulum also. That grandfather's clock also, it will swing like that. Or you can tell that the elliptical motion of the planet around the sun, that is also you can tell it is a non-circular motion. It is moving in an elliptical orbit, isn't it? So that both the direction and velocity, magnitude. So actually what is happening means during this swing, see if it is a simple pendulum or grandfather's clock also, when this pendulum moves, when it reach this position, velocity is changing from here, then the direction also changing, then it will move this side. Again you can see that from that place again it will come back. So you see every time the direction is changing, the velocity also changing. We know that when it reaches the top place here, the maximum we can tell that maximum potential energy. When it reaches this point, it is having maximum kinetic energy. So maximum kinetic energy, then kinetic energy becomes zero. There kinetic energy becomes zero. Again it is coming back. So that is what motion velocity is changing, magnitude of velocity is changing, also this direction also changing. So these are the three different ways a force can change the direction, changing the change the velocity of a particle, so that we will get a different motion. That is what we have seen. So the first one is magnitude of the velocity can be changed by without changing the direction, and the second one is the direction of motion alone can be changed without changing the magnitude speed, or the last one is both the direction and magnitude of velocity can be changed. Now the next topic is about the centripetal force. In the second unit you have seen about the centripetal acceleration, and there you have learned when a particle moving in circular motion, we know that there must be a centripetal acceleration which is acting towards the center. So towards the center of the circle there is a centripetal acceleration. When an object is moving in a circular motion, it is happening. So we know that. So what is happening means, we know that if there is an acceleration, there must be some force acting on it with respect to the inertial frame. Assume that here you can see we know that assume that this is a particle, and this particle which is moving in circular motion. So when this particle is moving in circular motion, we know that there is a acceleration towards the center of the circle. So if there is an acceleration, there must be a force also acting towards the center of the circle. So this force only we are saying centripetal force. So this is an inward force. There is an inward force which is acting towards the center of circle. That is what we can tell centripetal force. Always whenever there is an object moving in a circular motion, there must be a force which is acting towards the center of the circle. That is what we are saying centripetal force, and we can derive an equation from our centripetal acceleration. In the second unit you have discussed the centripetal acceleration means A is equal to V square by R. And from Newton's second law, you see this is what I told, F is equal to ma. We can apply Newton's second law in circular motion also. So we can tell that this is centripetal, and this is also centripetal acceleration. So we are finding the centripetal acceleration from Newton's second law. Centripetal force we are deriving from Newton's second law. We know that this you can keep 1, this you can keep 2. Now you can do substitute 2 in 1. So substitute equation 2 in equation 1, so that you will get FCP is equal to M. Instead of A you have to put V square by R. So this is the equation we are using. We are using what for centripetal force, and this centripetal force, that word meaning is what? Center seeking force. That's what I told. Any object which is moving in a circular motion, there must be a force which is acting towards the center of the circle. That is what centripetal force. And you can derive this equation from Newton's second law. For that we know that the centripetal acceleration A is equal to V square by R, and we are using Newton's second law, F is equal to ma. Now you see FCP, centripetal force, is equal to M into, instead of A you have to put V square by R. Now in vector notation, if you are writing this, we can write FCP vector equal to minus M V square by R into R vector. Here you can see minus because this force is acting towards the center. So which is opposite to the direction of motion. That is what we can use it minus. So this is what centripetal force. Now you have to know some fact about this centripetal force. What is that fact means? Actually, we know that many forces are arising, like gravitational force. This gravitational force is arising from the earth, gravitational force, then frictional force, then tension force. Like that, the tension is a force, Coulomb force, frictional force, gravitational force. These are the things we have learned before. These all are force which is arising from nature also, we can tell. So you see, from the earth gravitational force is acting, and from the string and all water tension, that force it is arising. And any object which is moving, I said opposite there will be a frictional force and Coulomb force. Between two charge particle, this Coulomb force is acting. Like this, different forces are arising from this nature, but our centripetal force is arising from these all type of force. Like I said, gravitational force. So gravitational force is the reason why there is a centripetal force. Tension is the reason why there is a centripetal force, and Coulomb force is the reason why there is a centripetal force. So because of this gravitational force and tension and this Coulomb force, from all these force, this centripetal force is arising. I will tell you how it is arising. Some of the examples given. For example, we know that this thing and all used to play. No, you can see that maybe in your childhood you have did like this, tying a stone and a rope and you are rotating. So during this whirling motion, we used to say that whirling motion. During this whirling motion of this stone, what will happen? You can see there is a force which is acting inward. This is what? Centripetal force, I told. So during this circular motion, there is a centripetal force which is acting towards the center, and this centripetal force is provided by who? Who is providing this centripetal force? Tension in the string. So this centripetal force is provided by this tension in the string. And you can see that some of the amusement park and all like this motion. You can see this in this amusement park, in this type of thing. Here this iron rope, when it is rotating, it will, you know that it will rotate in a circular motion. So here there is a tension in this iron string. In each iron string there will be a tension. So when it is showing circular motion, there will be a inward force. There will be a centripetal force which is acting inward, and this centripetal force is arising from what? The tension from the iron string. So this is the first thing. And the second thing is, you know that the motion of a satellite. We know that the satellite which is moving around the earth, that satellite is moving around the earth. During this time there is a centripetal force which is acting towards the center of the earth from this satellite. So when a satellite is rotating around our earth, there is a centripetal force which is acting towards the center of the earth, and this centripetal force is provided by who? It is provided by the gravitational force. And the third thing, if you are saying, means we know that here it is an example. You know that when a car is standing on this curve, not clear, you can see in page number 149 diagram. Actually current gone, that's what. In page number 149 you can see this diagram. One car is moving on a circular road. When a car is moving on the circular road, you can see that there is a frictional force between this tire and road. And here when it is turning this curve, there is a centripetal force which is acting like this towards the center. And this centripetal force is provided by who? This centripetal force is provided by the frictional force between this tire and this rod. And that is the third thing and all. And the last thing we can tell is planet. We know that some planets are orbiting around the sun, and there is a centripetal force experiencing towards the center of the sun even. And this centripetal force also, which is provided by what you see here, you can see the sun, and here you can see the planet. This planet which is moving around the sun, during this time there is a centripetal force which is acting towards the sun. And this centripetal force also provided by the gravitational force. That is what I said. Gravitational force, frictional force, Coulomb force. These all are the reasons why there is a centripetal force. So centripetal force means what? Whenever there is a circular motion, there is an inward force which is acting towards the center. That is what we are saying, centripetal force. And if you have seen that equation, it is centripetal force equation is derived from Newton's second law, F is equal to ma, and we know what is this A, centripetal acceleration. We have learned in the second unit, v square by r, and this v square by r we are substituting here. We will get the equation for centripetal force. FCP is equal to mv square by r, and here this is what in vector notation we are writing this equation. And for uniform circular motion, we can use this equation in terms of FCP equal to minus m omega square r. Actually, this equation, we know that the kinematic equation we have write it for angular motion, and for this angular motion we have to use omega square for angular velocity and mass and radius, and you can use this equation for uniform circular motion, centripetal force minus m omega square r. And I said this centripetal force is arising from what? This centripetal force is arising from other type of force like gravitational force, Coulomb force, and frictional force, and I said some example also. You can go through page number 147, 148 and 149, so you will get some ideas about this, and we will discuss more and about during the Zoom class session. Thank you all. Bye bye.